Hello and welcome to video 3 of Let's Learn C Programming for Beginners. So in this video I have chosen a computer to demonstrate various things on today. As no one commented to say what they preferred in the last video, I decided to choose the Commodore 64 here. So first off, I'll go over what I'll cover today. So first off, I'll go over the hardware of the Commodore 64 and the reasons why I chose it. So to follow along with the Commodore 64 code, you will need to see the video for installing the VBCC 6502 compiler, and also you will need the Vice emulator as well. So I will cover multi-file projects, so that will be having multiple header files and .c files. I'll then discuss what macros are. I'll then discuss pointers and hopefully easily describe these with some good examples. And then finally I'll show a demo of using all of them on the Commodore 64 to produce some simple animations, and also reading the keyboard for key presses, and also reading the joystick for joystick presses as well. So some useful things to get started on the Commodore 64 there, as well as some useful points for C program itself when working on consoles and old computers. So why did I choose the Commodore 64 today? Well, it's a good machine to demonstrate pointers on for a start, and it also will allow me to show a memory map of a machine as well, as we need to know the memory map on the Commodore 64 to be able to get it to do anything fun, like display hardware sprites, or to change its font set, referred to as a character set on the Commodore 64, or to change the screen and border colors. Basically anything significant on the Commodore 64, you need to send bytes into various memory locations to access its various hardware chips, turn them on, change the settings of them, get them to do stuff. And if you want to read the joystick or the keyboard, then you need to know again the memory locations, where to get those values from. So as an example here, this is basically an online memory map of the Commodore 64 here, and then it basically outlines the core addresses here. So it has like a hexadecimal value here and a decimal value here for the memory address, and then it has the description next to it. It says what various bits do. So the bits of a byte are basically treated as like settings or different switches. And then here it jumps straight to memory address 53248, which is the start of the VIC chip, or the video interface controller as it's actually known. This is the graphics chip basically of the Commodore 64. It allows you to directly turn on and interact with its hardware sprites. It also has registers for scrolling the screen as well, and changing the various graphics modes that it has. And then below that we have the SID address range. This is the sound chip of the Commodore 64. And then here it documents the various things you can get the SID chip to do by changing the values in these memory addresses here. So as it's an 8-bit computer, all of these are 8-bit address spaces here. And then below here we have the address of the first joystick port, and then the second joystick port here. And then the further you sort of scroll down here, it eventually wraps back round to the memory addresses in general here. So this is address 0 here, and then it basically goes down through everything, giving you a very detailed description of what's actually there at this memory address. And that will tie in nicely with using pointers, as we will be using those to do various things today. And it's a good demonstration of using pointers in the real world, in a real world situation, rather than me giving you a diagram of boxes and saying, oh, this now points to this box, whatever. You're more likely to get a good idea of why and how to use them, what they do, if I show you something directly with them. For example, changing the colours on the screen using a pointer, or getting the value of a byte at a specific address. So I could also have used the VIC-20 for this, but I thought the Commodore 64 would be better, as it has hardware sprites. The demo I'll give at the end will not be using hardware sprites in this tutorial here. This is just to give you a grounding in the key topics. In the next video I'll probably go for some more interesting stuff. We'll do some hardware sprites, change some character sets, go into multicolor mode for the sprites and tiles, maybe even do some sound chip stuff as well. So the Commodore 64 here was first released January 1982. It's got an 8-bit CPU in it. The frequency that it runs at varies depending on whether it's a PAL or an NTSC. So when CRT TVs were the thing, old style TVs, there was NTSC, which was North America, Japan, and there was PAL, which was basically the rest of the world. These are two different sort of screen formats. Basically, how those TV screens, basically how many frames per second they kind of run at, the sort of refresh rate. The hardware which run on TVs was basically split between the two different formats. So unlike today, some of the old computers would only run in one region. So it also has 64 kilobytes of RAM, which at the time was considered a large amount back in 1982. Most of the other machines for the time didn't have this much RAM. And it had the VIC-2 chip, which was a kind of game changer as well. This was like a powerhouse back in the day as well, as it featured 8 hardware sprites, whereas most machines at the time didn't actually have sprites. And to sort of simulate sprites, they had to do various graphic hacks to get them, and they were only sort of software. So what a sprite actually does is it's basically like an independent graphics layer. So you can have like an object move over the background without sort of having to destroy and repaint it. So it has screen resolution of 320 by 192 pixels. And I said it's got like a dedicated sound chip, the SID chip, which had 3 voices. And it also had various other enhancements which it could do, which was advanced for the time. And it also featured a multicolour graphics mode, which would allow basically 4 colours in one sort of tile, or 4 colours in one sprite, including the background colour, that is. It had like a colour palette of 16 colours, which was higher than some of the machines back in the day. Like, it's been listed in the Guinness World Records as the best-selling desktop computer model of all time. This was gotten off of Wikipedia here, so I'll take their word for that. So I will now get on to header files. So first off, what I'll do now is I will create a new program to demonstrate some of what I'm going to be talking about here. So the easiest way to do that is to just use the existing project here, and then we'll show you a quick way of doing this. So we're not going to need all this stuff in here. This was the previous project's name here, so we will rename that. And then if you open that up in a text editor, so on Windows you'll no doubt be using Notepad. So one of the things you'll want to do will be to, wherever you find this, go for search and replace, and just change that to your new name, replace all, and then this part here is the directory where it's going to be searching for all of the files. So this is basically the path, or the first part of the path here. Copy that. And paste that in there like that. And then save that. Now what you've basically done, so we delete that old program there. So the demo program, it will be using what's called a make file. So you will need a program called make to actually be able to use these. I believe it is covered in the Windows install. So now what we need to do is I will remove the old stuff here, and then I will give my project a new name. So this line here, where it says equals after it, this bit here is the name of the file that will be generated. I wouldn't give this too many characters, as this is going to generate a disk image for the Commodore 64 here. So whenever you need to change it, just change this part here, and then make sure you always have an asm.s file included as well. There won't be anything in here for now, but I will describe why that is there and why you need it in a later video. So we'll talk about header files. So when your project needs to grow, or when you actually want to develop something a bit more serious, then you'll want to sort of space out your project. And one way to do that is to use header files. So I'll remove this one here, and then I'll just bring up this a moment, and then we'll get rid of. I'll rebuild everything here. So here we go. Here's our brand new project here. Now, if we want to make a large project, then it makes sense to split it into multiple parts to keep it looking tidy. Now, the way to do that is to use header files. So you'll see here we have our entry function here, int main. So I'll create a new header file here, and then in here make sure you select the path to where you want it to be generated, and then we'll call it main.h, which is the standard naming convention here, and then make sure that this comes up here as well, the header guard. So what this does here is it stops the compiler when it builds from trying to generate multiple header files every time another module would include main.h. In this case, it's not going to be much. It's only going to be the main.c file here. It's probably not a lot I will actually be including in here. What I will do though is I will create another set of files here now. I'm going to be lazy, and although it says class, it's not going to be a class. It's going to be, what this will create for us is it will create a header file and also a module file as well. I always create like a utilities header and source here. Just make sure that it's going to dump them in the same location. And then we create those, and then we get rid of the C++ class stuff there. So our utilities header and module, they will basically be where we will define various utilities, data types and functions. So one of the things I always do is create some shortcut data types. In fact, it's not a struct. And we won't need anything larger than a short. And then what we will do in our main header file here is we will include the utils.h header file, and then in main we will include main.h, and that built okay, so that will do absolutely nothing at the moment here. So we could have, for example, in our utilities header file here, we could have a function called tile put, and then we will have tile X position, tile Y position, and then we will have so I always usually put the extern keyword on here, and the reason for that is this this header file utils.h, the utilities one, will be basically accessed by all other modules and header files throughout the whole project. And then in our file here, we define where the screen memory is there. We need to multiply the Y position by 40. So the Commodore 64, it has a tile-based screen. So I can show you some of this first off here. So we will go into the Vice emulator here. So here we go, here's our Commodore 64 here. And then what we have is we have the first off we're running the basic interpreter, and the screen what you see here is constructed of tiles, and these tiles have a memory map at location 1024, and I can demonstrate that by using a command called poke. What this means is send a byte to memory location 1024. So if I edit that, and you'll see by changing these numbers here, I can change the first tile there. And there are 40 tiles across by, I believe it's 24 down. So to get to the line below, we add 40. And that's exactly what this is going to do here. So with our offset, we'll add the tile X position there. So this is a memory address of 1024. So now what we need to do is we need to basically we need to set the memory address with the this tile ID here. So the way that we do this now is we I think that's right. Yeah, that should. So what we've done here is this ugly piece of code here. What that means is, first off, using the ampersand operator here, this means get the address of this variable here. In fact, no, we don't. I don't think we actually want to do that there. I think that's what we want to do. So what this should do here is this will use the value in screen memory here and then convert it to a byte pointer and then set the address of that to the tile ID here. So what that should have done there, so here's our C program here. So what we should be able to do now is and there we go. As quick as that. So what's actually happened there is we've set the full top line there to the character A, and as you've seen, it's switched to the lowercase font set there, and that's all that the that program did. So what this demonstrates here is why you use header files here. So one thing that I'll do another quick demonstration here a moment to so I will create the C string module and header pair. So lots of times the reason why you split these things up is you'll have like a header file and a source file to just look after one sort of object, if you like. So you have one sort of a data type or object, and then you'll have like a structure which defines its properties, and then you will also have all of the functions which act upon that one data type. So for example here, we'll have our C string data type here. So we will want to include our utilities header here. So we have the our type defs here, and then we'll have data here, and then we will use a define here to declare how large this should be. So as one line on the Commodore 64 is 40 characters, we'll say that the maximum size of our string is 41 characters, and then we will also hold a length value here as well, and then we will create a new C string here. And then what this will do here is this will generate, or rather it will take a C string data type here, and then inside this function here it will copy the string from the message variable here into the data here, and then it will also set how long the string is as well inside here. So we'll copy that function prototype, which is what it actually is, and then in here what we would do is we would then fill in the various parts of our C string here. And then you would probably want to use this from the utils function here, so you could in fact we would also this brings us into the another issue here. So inside the utilities function here, we would want to have some functions to draw that string to the screen. As we are on the Commodore 64, we won't be using the standard C header files here, so we won't be using stdio, because in reality those header files, the actual code which goes with them, takes up a big chunk of memory. When it comes to working with small machines, you want to avoid using as many of the C standard libraries as you can, because they basically take up chunks of memory to provide that functionality. If you don't use it, then there's no point including it. And the stdio header file, if you've looked at what's actually in there, so if we go in here, you'll see it's got all of these functions in here, and this will take up far too much memory, especially as we don't need most of these here. In fact, lots of these won't even be properly implemented for the Commodore 64 anyway. So one of the things in here which we would probably want to do is we would probably need to actually split these out into their own header file. So we will create another header file here. And then we'll copy those out and put those in here. And the reason for that is we need those types in here. Let's make sure that all compiles. Yes, it does. And the reason we've done that is we do not want to include the utils header inside the string header, because we need in here, we would need the C string header file itself. And the header file basically has a declaration inside of the string type. So if we want to use strings from the utils function here. Say we had a function called print, and then we said we wanted to print out whatever that string was. We need to include this data type here. However, if all of these were inside of the header file for utils, and string also included the utils header file, then this would kind of create a loop when the compiler was trying to build them, because what it's actually saying when you build these is all of the code in the module here depends upon the code pointed to by the other header file. So they would be kind of endlessly trying to include one another's functions inside the other's code when it was being built. So let's see whether the compiler will complain a moment. Okay, it's allowed it to happen. So what's actually happening here is C string is also including the utils header file here, and it kind of also, well, it's a bad thing to sort of, I don't know if I can demonstrate it here. On the desktop it would probably pick up an error here. I don't know whether it's going to generate anything here. So we'll copy this across a moment here. So what we'll do is we will set the length to 0. In fact, what I'll do is I'll come back to here a moment, because this is a pointer here, and obviously I will describe what these are in a moment. So I'll leave this for now, and I'll come back to that in a moment as well. So as I was saying there, you can think of header files as like blueprints for the compiler and the programmer. So what I mean, if I'll side by side these a moment. So what this is here is this provides a blueprint for any other module that includes this header file. It provides a blueprint of the functions which are available in the utils.c here. So you don't include C files, you only include the header files. So for example, the main.c should only be including other header files. In this case, it's including main.h, and main.h will act as a sort of repository or store which will include various header files which main needs to be able to carry out its work. And also, if there's any variables which are inside main, which it wishes to share with any external modules, then they can be included in main.h. So what the header file also provides is it provides an additional scope. So for example, in the utils header file here, we declare, so anything declared in a header file is potentially a global variable, which means it can be shared between other modules. However, so if we create a variable inside the C-string module here, this variable here is actually hidden or private inside this module here. It can't be accessed by any of the other modules because they shouldn't be able to actually see it. However, the development environment here will allow them to see it. So usually what I do is I put a Z in front of private variables, as this variable here should not be visible to any other module. If you want it to be visible, then you have to declare it inside the header file and give it the extern keyword here. Now this variable here can be accessed from anywhere outside. So that's another thing that the header files provide. They provide code scope. So this variable is obviously, you can think of it as like a publicly available function. Whereas if there was another function in here, say so say this just so inside of C-string here you cannot, no one else should be able to call that. So if I tried that in here, so the development environment will pick this function up, whereas in reality it should not be able to see that. This should generate an error. So here we go, this one here. Where is it? So now it's found that there's an issue with the including the header files here. And then where is it? So I'm not sure if this is because it's sometimes the errors and warnings are kind of garbled. So did I declare that? Oh no, it's complaining because I've created this prototype, but there is no code block to go with it, so we'll just do that to sort that one out. And then so let's get rid of that one there and then see whether it, there we go. That was because that header file was including the other, they were kind of trying to include various other stuff between themselves. And then what this has picked up here is this should actually be an error here, not a warning. So what this is saying here is it doesn't recognize this function here, so it's saying we are implicitly declaring the function add in here, which basically means that we the compiler can't find the function add anywhere that the main code block can access. So another thing here as well is we've not included the C string .h header in there either. So now that would build there. So where was I here? I was on about header files again here. So oh yeah, I was talking about scope. So this here is basically a private function which only the module itself can see. The header files and modules themselves in a multi-file project provide scope, which basically means which areas of the program can be seen by other areas of the program. Lots of times it makes sense to have private variables inside a module which can't be seen or accessed externally. And header files themselves, what they provide is they provide a function prototype here, which is externally visible from other modules and header files. And when you have a large project, you will need to be careful in the order that you have the header files, and always make sure that you have these header guards, which is what they're called, in your header files, as this prevents the compiler from including all of the code here multiple times in your project, which it will do if you don't have these on. Also, the some of the compilers, depending on the machine you're coding on, the compilers themselves might not actually pick up what the issue is, and sometimes the messages they give you are pretty poor, as they are not able to track down where exactly the errors are. So that's something to be aware of here. So the header files make it possible for you to grow your project, and it is the cleanest way to do so. this gives you a good example here of how to think about using the header files and their corresponding modules. For example, you have the data type, and then you have the various functions which act upon that data type, all sort of contained in one header file. And then you would put the extern keyword in front of the function or the publicly available variables, and that just says that this is declared externally, and because of these prototypes here, it means that it will only be declared once. The thing is, the header file doesn't actually care where this is actually declared. It just needs to be declared somewhere. So you can have, if you've got loads of different prototype functions here, if the list of them is really large, you've got like way loads of prototypes here, because the data type itself requires them all, then you can actually have multiple modules and stretch these functions across multiple modules. So you could have C string, and then you could have another module, and then call it C string 2. That also includes C string, and then you could have this function here, which is just for demonstration purposes here, and then both of these functions here can contain, both of these modules can contain the various functions here. So if you've got a list of loads of functions here, then you can stretch them over multiple module files if needed, which also obviously helps to keep your code tidy. Let's build that and demonstrate that it does actually work. And now I'll remove that, and I will delete that there. And then we'll get rid of that, as there's no point. You could just read that variable from the actual C string, so it doesn't make sense there. So yeah, that covers the header files there and their uses. So now let's get into another deep and complicated thing here, which you might have heard of before. So what is a macro? So you will, I've been using them for a while now, and this is an example of a macro here. Anytime you use the hash define statement there, this potentially is a macro. So the C compiler has a program or a component to it called the preprocessor. So a macro in C is a preprocessor directive with the hash define here, and it just means substitute a name with a value or a code snippet before compilation. basically before the when this program is being built, anytime there is a C string, this array size will be set to the value 41. So substitute the word C string max with the value 41. The compiler itself will never see C string max. It's not a variable. You can't change the value of C string max in the program itself. It's all done externally to the compilation process. Hopefully that kind of makes sense. So the C compiler has a component to it called the preprocessor. So this is a complex program all on its own. It's a text processing tool. So you'll see here all of these files here, they're all basically text files just given a .c or .h extension. The preprocessor, before the program is built, it basically reads all of the text from these files and tries to make sense of them. So it tries to work out the flow of the program code, and it will also look for any of the defines or the hash includes. It also does that as well. So it works out which files need to be included by the linker, which is another program part of the C compiler. The linker is responsible for working out how to connect all of the blocks of code together into one large sort of list or file for the computer to run. So anywhere there's like a hash define here, and then another example is the function type define. So another thing you can also do as well is you can create what's called conditional compilation. So in here we have C string max equals 41. So what you can do is, using the if define here, so what you could do is you can have, if C string max equals 41, then the C string data type will look like that. Otherwise it could have that. This is probably a poor example here. However, you can another thing for sort of like cross compilation, for example, so if defined, I think it's something like that. I think that's the correct defines. I'll just quickly check that a moment. So let's quickly, where are we? Is it that one? No. There's a good example of it. Ah, here we go. This is a good example here. So there's the defines there for not including the header file more than twice. Sorry, more than once. And then you'll see here some examples. So these defines here. So the C++ also has the preprocessor in it as well. So what this is catching here is if this is being run in a C++ program, then everything needs to be declared with the extern brackets C and that open bracket there. And then there's also this here which says if not defined. So if this is if the value of this is 0, then you can have other things being defined. So you can think of like if blocks. Anything where there's a hash, the preprocessor can basically, it's an indicator to the preprocessor to read. So you'll see here, in between these, you can have like functions themselves, where if a specific define is not detected when the program is being built, then it won't include these functions here. And there's like another one. So if you think of like you were sort of cross-developing for Linux, Mac, and Windows, you can have these defines here to basically create different functions and data types targeting specific operating system versions. Because all these files is they're basically just text files. So with the these preprocessor defines here, you say don't include this piece of text, don't pass it to the compiler, instead pass this piece of text. So the preprocessor is a powerful tool. The only thing to kind of be wary of is if you sort of generate any errors for the preprocessor, then they can basically be hidden, as they won't be picked up by the actual C compiler itself. So that can make debugging difficult if you get too in depth with the preprocessor directives and using various macros. So if you keep it simple, you should be fine. So example here, so this is an object like macro. So basically the same as this here. You can treat these as like constants. The only difference is, unlike a constant that the C compiler can pick up an error with, once the program is being built, anywhere this variable is declared, in fact I'll just remove the C string there, so let's put that back for now. So yeah, you can use it to basically declare variables in a header file, and all what happens is these defines, they don't actually take up any memory themselves, because all they're doing when the preprocessor crawls over the text, anywhere it finds this define, it just substitutes it for this number. So it kind of, it's like a text, how how can we put it, like well, it's a text processor basically, where you can get it to substitute certain text lines in your C or header files for others just before the program gets sent to the compiler. So as well as standard like object macro definitions here, it can also create function definitions here, and the same thing sort of applies with these. It will sort of calculate these functions at build time and return the values where they're needed. And when they're needed. So for example, this function here, so if you put that in here, so what this part here says is take in a variable, and then what it will return is that variable times itself. So all of these need to be bracketed as well, and they all normally need to be on one line. If you wanted to make it a multi-line function, then you need to add, I think it's the backslash, I'll have to find another demonstration program a moment, which has a load of them in. Let's think, where have I got some? Are there any in here? This is like a library I use here for on the desktop, and then see if it's got any in here. There you go, it's the Windows definition there. Like, this is a cross-platform one here. No, none in there. Okay. I'll just show you the one that I'll be using in a moment anyway. So here we go, these are some useful ones I'll be using in here. And then if I put these in here, which is where they live. So if you've coded on the Commodore 64, then there's the poke and the peek keywords. So as I demonstrated previously here, this is the C equivalent here of poke. So this here basically says, we could just change that to U8 and U16 there. So that's the same as what's happening here. Make sure it's happy with those. So this here is basically poking the tile ID into this screen memory address here, which is doing the same as this basically. This operator here basically means set the value of this pointer type, and the variable take that to mean the memory address. So you'll see here this macro here takes in a value, and then the value you pass in it calls the poke macro above, and then sets the memory address D020 in hexadecimal to the value you pass in. And I'll show you that here. And if we build that again. So what this is doing here is it will change the border value. There you go, and it's happening so fast that it creates the loading effect of the Commodore 64 there. So you could change that to the page one there. There you go, and you get the same effect to the screen there. So this demonstrates the usefulness of macros here. Basically, they kind of allow you to sort of create like a shortcut, or yeah, these functions are basically shortcuts where the results here. So this here, basically what's in here will be kind of pasted into the main while loop here. So the macros, basically they can give you like a constant values or like a constant function, and then this sort of code here, whatever is in here, is kind of like unrolled and pasted in here. So it also means that the tile put command here could literally just be replaced with the instead of this here, we could have we can just do that, and then we could just have we'll do that. In fact, we'll put that to border, because otherwise it will look pretty nasty. And then this is happening so fast here, it's literally drawn all of these tiles to the screen here. As there's a bug there. So if x is greater or equal to 40, then x equals 0. Let's build that again. So now all it's doing now is it's just repeatedly spamming these tiles on this line here. So those are the examples of macros there. So now let's get on to pointers. And then I can kind of you've kind of already seen these in use here, pointers. If I open this up again here, so like I said, this here, that there is saying get the memory address from at the value of screen memory, and that star says set the value at that memory address to the content of the variable in tile ID. So what is a pointer? It's basically a data type that points to another. So in C, a pointer normally must be defined to point at a specific data type. So in this case here, this here is a pointer of type U8. So basically this is an unsigned char pointer, and the way that you kind of distinguish that it's a pointer is usually you just put like a lowercase p in front of it. And then, as I've shown here, so this here now, this can only point to bytes, and on its own it would be kind of useless here. So what we'll do is, so we've defined our pointer, which will point to bytes in the memory of the computer here. So if you if I bring up the memory map again here, the Commodore 64, so it goes from 0 to FFFF, which is 65536, which corresponds to 64K. That is the whole sort of memory address range here. So for example, in hexadecimal here, if I type in FFFF, you'll see that's 65535. And then if you divide that by 1024, it says 63, but it's actually 64 bytes because it's not taken into account the 0 in the range. So normally when you sort of count on the computer, it's from 0 to the upper limit minus 1. So in fact, it's actually 65536 divided by 1024, which gives you 64K. That's the range 0 to FFFF. So coming back to pointers here, so this pointer, and in fact all pointers, they are really memory address variables, as in they literally contain a memory address inside of them, and the U8 part here just signifies what chunk of data it will actually return. So if you had a word pointer, which is an unsigned short, then what this would do is it would extract 2 bytes at a time from a memory location, as the size of a short is obviously 2 bytes in size. there's no reason why you would kind of need to do that on the Commodore 64 anyway. But on other machines, like on a 16-bit computer, that would be more useful. Obviously, that's not really that useful on the Commodore 64, as most things are byte in size. And the other interesting thing as well is so the size of an 8-bit pointer and a 16-bit pointer are the same because they are pointers. They are not unsigned shorts or unsigned chars. They are memory pointers. So to be able to point to the full memory range on the Commodore 64, they have to be 16-bit or actual, unsigned shorts themselves. And then if you go to larger computers, so on a 16-bit computer, for example, a pointer could be either 24 or 32 bits in size. And then obviously on the desktop computers of today, all pointers are in fact either 64-bit or 128-bit numbers or data types, because they have to be able to reach the full range that the computer the program's running on can actually see. So with a pointer here, it can be used to basically pass the memory address of a variable between various functions, as the normal default for functions is anything you pass in as a parameter is just a value. So that means that value only exists inside the actual function block it's part of. Whereas if you want the variable itself to be altered by the function, then you have to pass the function a pointer to the data type. For example, in the print function here, this is a pointer to the C string type here. Now, whenever you work with pointers, it's basically, so if you're working with like a pointer of a struct, then instead of the dot operator, you use the pointer operator. And then you can basically change the value of what the pointer is pointing at. However, if you were passing in a standard data type, then to operate on this here, you have to use the asterisk data type here. So if I scroll down here, so to change the data located at a memory address of a pointer, you have to use the star operator here. So you'll see the star operator is used to tell the function that it's a pointer, but to change the value of the pointer, you have to use the star operator. So what this would do now is the value of tile Y would be changed inside this function here, and when something that called this function returned, the data type it passed in would be altered inside here. Now, to actually pass a variable to a function which takes a pointer, say we had, there we go, my value here. So my value equals 5, and then if you called the print function here, then to pass this variable by reference, as in pass the address across, you use the ampersand or and symbol here. And then you would do the same for if we had a C string. For example, and we wanted to pass both of these to the print function, then you use the ampersand symbol in front of each of them to indicate that what you're actually passing is you're passing the memory address. So now that we have the memory address, we can basically change the value or the contents of it. So another thing you can do with pointers here is talking about the C strings here. So if you look in the string here, you'll see that it actually has an array of U8s in here. Now if we wanted to print that out, we need to read all of those from the array inside. So we would need another pointer here, say p tiles, as in point to the tiles, and then take in our pointer of a string. And now what this here does is it now points at the first unsigned char in the array inside the string. And then what you would do is, so we'll have a counter variable here, and then we want the tiles value here. Is we could either, best way is to use a do while loop. While tile value is greater than 0, and then what you do is you use tile value and then you return the value of the memory address that p tile is pointing at. So p tile is pointing at the start here to the first char in this array here. What this says here is, at that memory address you are pointing at, give me the value. So now the tile value here holds the value of the first letter in this string here. And then what we can do is tile put tile x comma tile y, and then tile value there. And now what we need to do is we need the pointer to move on to the next value in the array. So to do that, you just do that. So we don't really need n there, actually we can get rid of that. In fact, what we'll do is we don't want to, we'll say if tile value is greater than 0, then print it out. otherwise exit the loop. And then we also want to update the value of tile X there as well. So now this print command should actually work. Oh yeah, this another thing to note here is to get it to display the correct tile, we need to do this. I'll explain that in a moment. So we do that there, and then we'll say print, and then we'll say, oh, is it 10, 2. Oh, we need a C string now. Okay, so now what we need to do is we need to fill in that function there, which comes back to the pointers here. You'll see that this takes a pointer here, so this function here basically will set up our new C string. So we already have a char pointer there to our message. So what we need now is to do a do while loop again. And we will end our string if the value of 0 is found. So tile equals star message, and then we'll plus the message pointer there. So this here, all it actually is this is actually an array of chars. And then we'll say oh yeah, we need another pointer here. So another thing to note as well is the declaration in these functions of new variables has to be at the top on the old machines, as that was the way that the C compilers, the versions worked for them. So we need to take the contents of the passed in string, take a tile off of the top, and then we basically copy the value to the address that pdata points to here. So in this loop here, we are actually setting the value, whereas in this one here we are taking the value and plotting it on the screen here. So depending on which way round these two are here, this one here is taking the value from the pointer, and this way round it's setting the value of the pointer. The what it's pointing at is basically changed. And then what we do, if tile is greater than 0, in fact no, we'll just leave it as that. Although what we want to check for is we want to make sure that the value of n doesn't exceed the maximum string size here. There we go. This will set the last byte that the string is pointing to 0 if it's too long, and exit that. And then we want to obviously increment the byte that the P data is pointing to here. And then at the end here we can say the length equals n. Minus 1. Let's build that. So that will set our new C string. So we'll do C string new, my string, and then we'll say hello C64, and then we'll print that out there. And hopefully I've not put any bugs in there, and I don't see it. Let's try putting it down further. It's because I'm not actually writing anything there. Let's try that again. So that's the actual text there, which it's garbled. Wonder if that's because and then we probably will want to in fact, what we want to do here, if only want to change that if that's the case. So if it's a alphanumeric character, then we do that. Nope. Okay, let's see what's going on here. So we've took the tile value there. If it's greater than 0, so is the C string mangling it up? Let's have a look. Oh, I know what it is. I know what it is. I encountered the issue earlier. The other day, we that's the right one. There we go. So it's in lowercase there, and it's also flipped it to be inverted as well. So the reason for that is it's how the Commodore 64 handles screen code there, the tile screen codes. So that that demonstrates working with pointers there. Hopefully you understand them now and their usefulness. So in where are we? To get the address of a pointer or the address of a variable, you use the and symbol there. When you work with a pointer, the asterisk character before the pointer name will give you the value contained in the pointer, and then you can use the normal sort of like arithmetic operators like plus plus or multiply or divide or whatever. But if you don't have the star in place, this will just change the memory address that the pointer points to. So these little demonstrations here hopefully give you a good understanding of how pointers work, how the why you would use header files and what have you. So now let's have a look at the actual main example here, example program that I want to show today, and what I've got in there. So I'll build it first and then I will talk you through So what we're doing here is we are plotting tiles to the screen again here. It's an example of printing out a string here, and then by reading memory at certain addresses here. So this key peak here, the value it returns here is the scan code for the key that you're pressing. By default, the return value is 64. However, when you hold a key down on the keyboard, the number changes to the scan code there. So this is useful if you want to draw a tile at a certain memory address on the screen and you wanted to sort of move it around. And then I also have here the joy port being read as well. So you can see here the when you press the various directions on the joystick, the letters change here. Again, in the next example, I will show some more advanced stuff on the Commodore 64 here. So in here we have the definitions for the graphics that you've just seen here. Basically all I did was there's like one of the tile graphics for the Commodore 64 is a solid square. No, not that one. So in Libra Sprite here, if you look on these presets here, you'll see it has one for Commodore 64. And then if you load that in there, you'll see that these colors here correspond to this color palette at the top here. And then basically I plotted these characters here. These are 16 pixels by 16 pixels. And then using a program I have called DS to tiles, I basically converted the pixels into byte arrays, and then each of these numbers here corresponds to a color here. So one thing I have in here as well is this is a lookup table. So on the Commodore 64, as I said, there are 40 tiles going across the screen. So a fast way to calculate the screen line is to create what's called a lookup table of pre-computed values. Come on. And these are those values here. So these offsets here are multiples of 40. And then here's some useful functions in here. So this function here will basically plot tiles on the screen to represent the pixel colors. So as well as the screen memory for a tile, there is also a color memory map as well. And each color can be one of 16 values, which are these values here. So these are the definitions for the bat, and these are the definitions for the Viking. So I will not say any more now about the Commodore 64. I will give you this example program here to have a muck around with. If you are sort of coding on the C64, then I recommend you get a memory map. I will include this one in the folder with the source code for this program here, and you'll probably want to find some documents online for the Commodore 64. For example, you'll be able to find the user guide for it here, which will give you some info on the Commodore 64 itself. Lots of the stuff in here can easily be sort of converted into C. So it's got the colors there, and it's got like some print symbols here. So there's two different ways you can kind of display stuff on the Commodore 64. You can either poke directly into its screen memory map, or you can use the basic printing routine that the interpreter uses. and there is a function here. If you treat this like a function, so this this command here actually executes an assembly language program in 6502 here, where it basically loads the accumulator, which is what's happening here. The accumulator is an 8-bit register on the 6502 CPU used for various calculations, and then the equivalent of a function call in assembly language is called jump to subroutine. And on the Commodore 64, if you set the accumulator to a value and then jump to subroutine FFD2, it calls a internal function which will print out a string of characters for you, or just one symbol. So the Commodore 64, it has a command called print, and then this symbol here, for example, 147, what that will actually do is it will actually call a function. It substitutes some symbols for actual commands, and that symbol there, if I find it here, where is it? So these are the screen codes I was talking about here. You'll see 1 corresponds to A, and then there's things called the ASCII and CHRS codes here. And if you call that function FFD2 with the accumulator set to one of these values here, it will either print out a character or it will run a small block of code. For example, there's this one here, CHRS5, will change the printed out text color to white. And then this one here, 147, is a quick way to actually clear the whole screen on the Commodore 64. So if I do this one here, sorry, you'll see it clears the screen. Now to do this in our C code here, I have an array in here of useful symbols. So this one here is the clear screen symbol here. This is 147 in decimal. And then this enumeration here, basically these line up with these here. So you could use that print function, print a symbol to change a color, or move the cursor to print to another line, or use the print at function, which will actually poke the string into memory. And then there's a command here to print symbol, which just takes one of these symbol IDs. For example, where are we? There we go. Print symbol white, and then clear the screen. And then the print at function here just targets the location where these strings will be output. See that they're all lowercase here. So I'll leave this program description for now, and I will see you in the next video, where I will go over using some sprites and tiles, and I'll try and think of some other things I've not covered yet. I think I've pretty much covered all the main useful things that you will need to get started now. In the next video, I'll just sort of go over some useful sort of data types that I normally use. So we'll move some sprites around on the Commodore 64, maybe do some sound, some tile graphics to get started using C programming on these machines. So one thing you might have noticed as well is I didn't include any C libraries at all, as most of the time on these machines you literally need to actually know the machines to get coding, especially when it comes to the 8-bit machines. So thanks for watching, and I will catch you in the next video. If you have any comments below about anything I've covered, then just let me know, and I will catch you in the next video.